you have your carbocation intermediate. Now these steps, it takes place in two steps, take place at different rates. One of those steps is a lot faster than the other one. Which do you think will be the fast reaction step? This first one or the second one? Second one. Because I have the positive charge here that very quickly. So the leaving group leaving is going to be a very slow reaction step. And so since this is a slow reaction step, we say this is the rate determining step. Therefore, the rate is only dependent upon the substrate. So that's why it's unimolecular. So it doesn't matter what nucleophile you have or the concentration of your nucleophile. Okay, it'll have no effect on your reaction rate. So if you double the concentration of your substrate, doubles the reaction rate. Double the concentration of your nucleophile, no effect on the reaction rate. Double concentration of both, it only doubles the reaction rate. And because it goes to this carbocation intermediate, the more carbons you have here, we know what affects the stability of a positive charge on a carbon atom is other alkyl groups that can donate electrons to an inductive effect. So the more carbons you have attached to it, the more stable that positive charge, the more likely it is to form. And so if we look at the reaction rate for this one, tertiary is going to be the fastest, then secondary, then primary, much faster than methyl. How does that compare to the SN2 reaction? Exact opposite, right? The SN2 reaction, methyl group was the fastest. So you kind of see the substitution is going to play a role in what mechanism it takes place in. Methyl group, SN2 reaction. Tertiary SN1 reaction. Let's go ahead and look at some homework. (11-8). What product would you expect from reaction of S,3-chloro,3-methyl-octane with acetic acid? So there's octane. 1, 2, 3, 4, 5, 6, 7, 8. 3-chloro, 3-methyl. So I'm going to assign priorities here. So here's 1, 2, 3. So my methyl group is my number 4 priority. So that is counterclockwise. So that is S. 3-chloro, 3-methyl-octane. So here's acetic acid. So this is a neutral nucleophile. So remember, we have a neutral nucleophile, some lone pairs of electrons where you can lose a hydrogen. What has a lone pair of electrons where I could lose a hydrogen from it? This oxygen here, yeah. So that's what substitutes on in place of my chlorine. Since this is a tertiary, it's going to go by an SN1 reaction. So that means leaving group leaves first. So then my acetic acid can attach from either side. So I get a racemic mixture. Alkyl groups stabilize the positive charge through an inductive effect. Therefore, most SN1 reactions take place when the substrate carbon is tertiary. SN1 reactions can also take place through allylic and benzylic carbocation intermediates due to increased stability through resonance. So this allylic and benzylic are the position adjacent to it. So if the halogen is attached directly to your double bond, unreactive. If it's one away, it can take place through an SN1 mechanism. Because if you look at your carbocations in, it's stabilized through resonance. So this is allylic benzylic. Benzylic is an extra carbon attached to your benzene ring. So again, that can be stabilized through resonance. So you can just move the electrons around. To get those different structures. SN1 reactions take place more rapidly in polar solvents than in nonpolar solvents. Polar solvents tend to stabilize the carbocation intermediate. So in this case, remember SN2 was polar aprotic. Here it just has to be polar, so polar protic solvents work well. And so this is probably a reaction known as sobolysis, where your solvent and your reagent that substitute on your nucleophile is the same thing. So you have a large excess of this, and so you have a polar protic solvent, which is going to favor the SN1 reaction. Since the nucleophile is not involved in the rate limiting step, all nucleophiles are equal. So nucleophiles without the charge are just as effective as negatively charged ones. If you look at your leaving group reactivity, we have a new leaving group here. That's OH has been protonate, so H2O is going to be a leaving group. And it's going to again increase with size. Let's look at some problems. 11.11, 11-12. So 11-11, rank the following substances in order of their expected SN1 reactivity. So what I'm going to look at is the substitution. So this carbon's attached to one other carbon, so that's primary. This one's attached to two, it's secondary, but it's also adjacent to a double bond. So it's adjacent to the double bond. That makes it allylic. This one's attached directly to the double bond. So that makes it vinylic, and those are unreactive. So I'm just going to go ahead and call that one the least reactive. And then this one's attached to two, so it's secondary. So the most reactive then, the most substituted, I have two that are secondary. One of the secondary is adjacent to a double bond, so it can be stabilized to residence. So that's my most reactive. And then it'd be my other secondary. So we're kind of put it all together for substitution now. So tertiary alkyl halides are too sterically hindered for attachment from the opposite side by an SN2 mechanism, but able to stabilize the carbocation intermediate in SN1 reaction. Methyl and primary alkyl halides are not substituted enough to stabilize the carbocation intermediate in SN1 mechanism, but are less hindered for attachment to an SN2 mechanism. Let's look at some other examples. Look at 11-12. So 11-12 says 3-bromo-1-butene and 1-bromo-2-butene undergo SN2 reaction at nearly the same rate, even though one is a secondary halide and the other is primary. Explain. Well, if we look at this, let's look at the resonance structures from the carbocations for each of these. So if I look at the resonance structure for this one, I have those two resonance structures. Okay, so I took the bromine off here, positive charge. These two electrons are donated over there. Now, if I do the same thing over here for this one, move that double bond here. How do those resonance structures compare? You see that they're their exact same resonance forms. So the carbocation intermediate formed is exactly the same thing, since it's allylic like that. And so that's why they undergo a reaction at the same rate. Look, this is one of the work examples here, then I'll work the other one. says predict whether each of the following substitution reactions is likely SN1 or SN2. So, on your exam, I probably won't be this nice to where I give you the product. I want you to, I wouldn't give you the product and I'd say, show the mechanism or draw the reaction product. And you have to figure out just from looking at this what mechanism it goes through. But if I look at these, you know both of them are substitutions, something substituting on. So here's my nucleophile. Remember, AC just stands for CH3 C double bond O. So that's what this nucleophile is. So first thing I'm going to look at is the substitution of my substrate. So it's secondary, and it's secondary and benzylic is adjacent, so it can stabilize that positive charge. Plus I have polar protic solvents. Remember, polar protic solvents don't work well for an SN2 mechanism. So since it's secondary, benzylic, and polar protic solvent, that's going to be an SN1. So I get the racemic mixture there. This next one, again, here's my nucleophile OCH3 minus SN2 because it's primary. And this is actually a polar aprotic solvent. In most cases, if you see some kind of a strange acronym here, like DMF, HMPA, those are probably going to be, even if you don't know the structure of them, they're probably going to be polar aprotic solvents. Most of the ones that have acronyms like that are aprotic. So let's look at 11-13. Why do you think this one is? SN1 or SN2? So if I look at my substrate there, well, it's an OH group, and we saw that OH groups are not good for leaving groups for SN2. You have an acid, and so that's going to actually become protonate and become an H2O leaving group. So it's H2O leaving group, secondary, and also allylic, it's adjacent to a double bond. And also polar protic solvent. So polar protic solvent, H2O leaving group, secondary allylic, all point towards an SN1 reaction. Go ahead and write that down. Now if I look at B, B is primary. It's also adjacent to a double bond, so it's also allylic. I have my nucleophile here in a polar aprotic solvent. So since it's a polar aprotic solvent in primary, even though it's still allylic here, it's a 2 mechanism.
Put it back to that folder for just a minute.
Put it back to what?
That column.
What we're going to look at now is elimination reactions. Elimination reactions involve the formation of an alkene through the loss of HX. Elimination reactions generally produce a mixture of alkenes, but usually the most substituted alkene will be formed as a major product. This is known as Zadzis rule. The use of a sterically hindered strong base normally produces the least substituted alkene as a major product. That's known as Hofmann elimination. Let's see what a sterically hindered strong base is. Strong base, oxygen with a minus charge on it. Okay. Sterically hindered strong base is if that carbon with the oxygen with minus charge on it is tertiary. So like the tert butoxide ion would be an example of a sterically hindered strong base. So if I look at 11-15, ignoring double bond stereochemistry, what products would you expect from an elimination reaction of the following glycol halides? Which product will be major in each case? And so wherever I have my halogen, I'm going to form a double bond between that carbon and adjacent position, lose a hydrogen from that position. So it'd be a double bond could go here. Or it could go to the right side of where I have my halogen. So I'm looking at the substitution, so I'm looking at my C double bond C, and seeing how many other carbons are attached to my C double bond C. Where on this side I have one, this side I have one, so that's a di-substituted alkene. Here, this side I have one, here I have two, so that's a tri-substituted alkene. So it's the most substituted, so that would be my major product. Let's look at B. So here's my carbon with my halogen. So my double bond can form between that carbon and the adjacent position. Here I have three adjacent positions. So I have three possible products. So I just went to each adjacent position. So I went to the left, to the right, and then going down. If I look at the degree of substitution on my C double, I'll see this one's attached to 1, 2, so that's tri-substituted. This one, 1, 2, 3, 4, that's tetra-substituted. And this one, no carbons here, 2 carbons on this side, that's di-substituted. So tetra-substituted be my major product. Eleven 16, why alkyl halides might the following alkenes have been made from? So you have to put your halogen on there, so you look at where your double bond is. So that's where I'm going to put my halogen. So there's 2 carbons there. I can put the halogen at either position. If I put it here, there's 2 adjacent positions. So my double bond could go here or here. But if I put my halogen here, it can only go to one position. That's the product I want to make. So it's going to be better if I put it at that position so it only forms one product. Here, again, here's where my double bond is. I could put my double bond at either position. If I put my halogen here, my double bond could go here or here, and this would be more substituted, and so this would be a minor product. But if I put my halogen here, it could go here or here, but that's the exact same thing as this. So putting it up here, still the same structure as that. So that is where I would want to put it. Well, I still have some of chapter 11 to cover, big part, chapter 11. And so homework will not be all due on Sunday. We'll put the homework due Monday night, but I would make sure you get all of chapter 9 and 10 homework done before Monday. Okay, I'll extend chapter 11 homework only. Okay. That's why I said I wasn't telling you. Look at the notes on Blackboard.
Oh.
Do the post.
See, I was like 10 minutes late to the lab, so I probably missed that. Oh, yeah. I'll
Look
do
on
it.
Blackboard. It's something on there. Explain it step by step.
All right, thank you.
Yeah.
On 11:15, there's the tri-substituted and the tetra-substituted and the di-substituted, but we don't know how you got that. Substitution part.
So I'm looking at my C double bond C. Okay, so I'm looking at how many other carbons are attached to that C double bond C. So here I have one carbon attached, two carbons attached, three carbons attached. Tri-substituted. Again, looking at my C double bond C, one carbon attached, two carbons attached, three carbons attached, four carbons attached. Here's C double bond C, one carbon attached, two carbons attached.
Alright, thank you.
Is the test still gonna be on Tuesday? But is Monday still gonna be the test review, kind of?
We'll see how far we get.
Cause I'm gonna miss all day Monday, we recorded still. I'll send an email to remind you guys.
Is the final on the 28th or the 29th?
Yeah, what's the two? It's on Thursday, I think.
Thursday?
I think the syllabus is 29th, isn't it?
Did it?
Yeah.